The goal of the whole chapter would be to put quantities to chemical reactions. And so we've looked at how to convert a bunch of different quantities, grams and moles and molecules and all of that kind of stuff. And so now we're going to switch over and focus on the chemical reaction side. What is a chemical reaction? How do we write chemical reactions? How do we balance chemical reactions? Does that ring any bells to you? Have you had to do balancing chemical reactions before? Yeah? Okay, so it might be a little bit new, it might be a little bit review, but that's really what our topic's going to be today is how can we satisfy the law of conservation of mass with a chemical reaction, okay? So chemical reactions are a process which substances are changed into something new, right? That's the key part to it being a chemical reaction means that something new is formed. Okay, it's changed into different substances. So melting ice to liquid water is not a chemical reaction. It's not a chemical change, okay, because nothing new was formed, right? It's still H2O. A chemical reaction would be where we take hydrogen gas and oxygen gas and we make them water, right? That would be a chemical reaction. So chemical reactions are made up of two distinct parts, the reactants and the products. Do you remember how a chemical reaction is set up? Which one goes on the left and which one goes on the right? The reactants go on the left. So if you have some compound A plus some compound B yields some compound C and D, that would be a chemical reaction. The reactants sit on the left because they are the ones doing the reacting. And then the products sit on the right. They are the things that are produced. Do we feel comfortable with that? Do you remember what that arrow represents? Say it again. Change in, yields, produces, equals, right? Any of those things would be true. In its most basic definition, it means yields, right? It produces this. So we put two reactants together and it yields these products, okay? All right, so these are a couple of what we call indicators of chemical reactions. I think we talked about these briefly earlier in the year, but these are things that we can know a reaction has taken place if we see these things. If we mix together two clear liquids and it turns a color, that would tell us that a chemical reaction has taken place, right? There are other examples of that not within liquids, right? If I have rust form on a piece of metal, that would be considered a chemical change, right? That is oxidized iron that has formed what we consider rust. And so that is a product of a chemical change. If it's endothermic or exothermic, do you know what endothermic or exothermic might mean? Good. It either takes in heat or it puts off heat. Did we talk about examples of those? Okay, those would be like examples of like those hot hands that you might put in your gloves, right? We talked about this where you have to shake it and it makes a reaction, or an ice pack that you have to pop it, right? And it makes a reaction. Those are endothermic, exothermic. It could just be things that you mix together and it starts to heat up, right? If you have a formation of a gas, so if I put together two things and they start to bubble, that would be an indicator of a chemical reaction. And then the formation of what we call a precipitate. And a precipitate means a solid is formed out of the mixing of two liquids. Okay, we're going to do a reaction, a lab with a precipitate here at the end of this chapter. But if I put together two liquids and it starts to become chunky, right, or if there's solids that form to the bottom of that, that tells us that some sort of reaction has taken place. And one of the products is no longer soluble in water, right? That's what happens in a precipitate. So those are what we call indicators, okay? So you might even write that up there. These are indicators of a chemical reaction, okay? They indicate, there's indicators, that word. That a chemical reaction has taken place. Okay? All right, some characteristics of chemical reactions. They have to have correct formulas for reactants and products. Otherwise, we won't be able to satisfy the law of conservation of mass. So if we are supposed to have potassium sulfate, and I write K2SO3, that's not potassium sulfate. What is it? That's potassium sulfite, right? And so if I write my formulas incorrectly, I'm going to have a hard time balancing my chemical reaction, right? Because I won't even have the right number of oxygens present. So when we write out our chemical reactions, we have to be super, super diligent about making sure that our formulas are correct. Okay? When we say the law of conservation of mass must be satisfied, do you know what the law of conservation of mass says? Mass can not be created or destroyed. And so all that means is that if I put in 4 hydrogens into my reactant side, how many hydrogens have to come out on the product side? 4 hydrogens. They might be rearranged. They're probably bonded with something else, but they have to be equal to the amount that went in. That's all the law of conservation of mass says. And that's the principle that we are trying to satisfy when we're balancing reactions. And that's really our goal today, is making sure that our chemical formula or our chemical reaction is true. Right? Essentially, we're trying to write the recipe for a chemical reaction. We have to make sure what we put in is going to be what we get out. Right? We're checking to make sure that recipe is written correctly. Okay, some symbols you might see used in chemical reactions, S, L, G, and AQ. So I might see H2O written like this with an L next to it. What do you think that means? Liquid. So S must be solid, liquid, gas. And then do you know what AQ means?
Aquarium.
No. AQ means aqueous, which means it's been dissolved in water. Okay, so AQ means aqueous. And it means whatever substance is listed has been dissolved in water. And water is not a part of the reaction, but it's been dissolved in water, so now the ions are split. So if you see NaCl aqueous, that means that we've got salt water here. And the water is not part of the reaction. It just has split the sodium and the chloride ions so that they can bond with other things. Okay, and so it allows the reaction to take place in water.
So it can still be divided?
It can still be divided. What do you mean?
Like you could still take out any of the aqueous, anything that's aqueous can still be taken out of the water?
Yeah, they're individual ions now. So sodium ions are floating around and chloride ions are floating around, and they're ready to bond with other things.
Okay.
Mm-hmm. Okay, and then we will use what we call coefficients. What does it mean if you have a coefficient in math? Right, if I have this value right here, what's the coefficient? 2. It's the whole number. Okay, for us, it's going to be whole numbers. In math, it might not be a whole number. But for us, it's going to be a whole number that sits in front of a chemical compound. So it tells us the number of molecules needed to balance or the number of moles. Remember, we talked about that ratio stays the same. So if I have 2 H2O, that means I have 2 water molecules. But how many total hydrogens would I have in this scenario? I would have 4 hydrogens, right? 2 per molecule times 2 molecules. And how many total oxygens would I have there? 2. Okay? This coefficient also tells us that I have 2 moles of water that's going in. So we can think about chemical reactions on the molecular level, 2 molecules of water plus this, or we can think about it on the molar level. I'm reacting 2 moles of water with this. It's the same ratio, it's just a different scale, right? Little picture, big picture type stuff. Okay, we will mostly deal with moles, right? Big picture. Okay, I'm going to go through a series of the types of chemical reactions, and then we're going to get to balancing them. So the types is you're going to be able to see a chemical reaction and identify what category it fits in. There are several different categories of chemical reactions. Some of them might sound familiar to you and some of them might be different. But the first type of chemical reaction is called a combustion reaction. Have you heard that word before? What does it typically mean? It's burning, right? Or an explosion, but most of the time means it's burning. So a combustion reaction is when something burns with oxygen gas, it combines with some sort of hydrocarbon. Okay, a hydrocarbon is any sort of combination of carbon and hydrogen atoms. And its products are always CO2 and water. Okay, combustion has a very specific set of principles that you can follow. So combustion reactions are really easy to identify because it will always have oxygen as a product, carbon dioxide and oxygen as a reactant, carbon dioxide and water as a product, and it will always have some sort of hydrocarbon at the beginning as well as a reactant. Okay, so combustion reactions are simple to identify for those reasons. This hydrocarbon could have more things bonded into it. You could have C3H8O, and it would still be considered a hydrocarbon. It's just got some extra things added onto it. Sure. Okay, so with our types of reaction, you would identify this as a combustion reaction. Okay, the next type of reaction is called a synthesis reaction. Do you know what the word synthetic means?
Like fake.
Like fake or man-made or produced. Synthetic means all of those things. And so a synthesis reaction means something that is made, something that is built up. Okay, so synthesis is when two or more simple molecules combine into a more complex molecule. We take two small things and we build them up to make a bigger thing. So it has the base formula of some compound A plus some compound B yields some new compound A, B. And then I give you a real example underneath there. Iron plus sulfide equals iron sulfide. Here produces iron sulfide. But it's got a very basic general reaction. Okay, so you might want to know this guy right there.
What happened to the 8?
Reaction? And what does it mean if something decomposes? It breaks down. And so that's what's happening here. We have a complex molecule and we break it down into two or more simpler molecules. So we take some complex compound AB and we break it down into two or more simpler compounds. So synthesis and decomposition reactions are opposite of one another. Synthesis is to build it up and decomposition is to break it down. Okay, do we feel okay about those three categories? Okay, the next two get a little more intense, but are I think simple to pick out as well. The next reaction is called a single displacement. Okay, sometimes you'll see them called replacement even, but I like displacement fine. Okay, single displacement reaction is when one element trades places with another element in a compound. So we see maybe the two cations switch places or the two anions switch places, but not both, right? We see one element take the place of another in the reaction. So here, if you look at the example I gave you, you have sodium chloride plus potassium yields potassium chloride and sodium. What are the elements that switched places here? Potassium and sodium switched places, right? Potassium went from being by itself to now be bonded with chloride, and now sodium's by itself. So we saw one swap. Okay? Single displacements, I think, are sometimes the trickiest to pick out because it's a little, I don't know, it's just tricky to figure out which one is switching. All right? All right, double displacement reactions are going to be our most commonly used reactions right here. We're going to use them a lot. They're used a lot in the lab. But double displacement is when both the cations and the anions switch places. The cations and the anions switch places. They both get new partners. Okay. Oh, and do you have a question or no?
Yeah.
Yeah.
Would it, is it the same thing if the B and the C were like flipped around, like the B came first, or is that?
Yeah, the only reason it's written like this is because typically these are cations. And so, remember, we always write the cation first. So it doesn't really make a difference if it went AB plus C yields whatever. It could be any of those things. Yep. Okay, double displacement is when cations and anions switch places. So everybody gets a new partner here. Okay. Here is an example, and this is actually really important why it's written this way. I'm going to write it a little bit bigger. Some compound AB plus some compound CD yields AD plus CB. And these are written in a particular order for a particular reason. If these are ionic compounds, which we assume they are, this is a cation and an anion. A cation and an anion, right? That's how we put together ionic compounds, with cations first. Would we agree? And so when we put our two products together, could we have a compound of A plus C? No, because I can't put two cations together. And so what has to happen is the cation from the first and the anion from the second form a new compound. And it's written AD, not DA, because why? Cation has to come first. And so now we're going to take C and B and put them together. But again, it's not written BC, it's written cation, then anion. So there is a reason for how those are written that way. Okay, so in a double displacement reaction, we will always see the outsides come together and the insides come together to form two new compounds. Could I have written my products CB plus AD? Yes, right? The order in which we list our compounds and our products, that makes no difference. But we do need to make sure they have the correct partner and they're written cation, then anion. Okay? So check the example I gave here. Lead nitrate plus potassium iodide yields potassium iodide. So we would see lead come together with iodide, and we would see potassium come together with nitrate. Is that what we see as our products? PB and I, and K and NO3. We see those come together. Agreed? Now, why is it that I doesn't have a subscript here, but it has a subscript here? Any guesses? It's okay, all good thoughts, but this has to be built to be balanced. Lead has a charge of +2 and iodide has a charge of -1. So to get it to be an ionic formula, it has to be PbI2. So just because it does or doesn't have a subscript here doesn't mean that that same rule will apply as the product. We're going to look at that later. But when we go to build these new products, we have to build and balance those just like we know how to build ionic compounds. We know lead and iodide are going to come together. We've got to balance them first, and then we'll look at the whole reaction. Okay? Okay, if they are existing by themselves in pure form, they can't exist as single elements. They have to exist in a pair with themselves. So these are called diatomic molecules. Okay, which means basically these elements are too unstable to exist just on their own. They have to exist in a pair. So it's like a buddy system thing all the time. There are 7 of these diatomic molecules. I'm going to list them, but then I'm going to show you how to pick them out on the periodic table. Okay, so 7 of them. Hydrogen is 1, so it has to be H2, N2, O2, F2, Cl2, Br2, and I2. So there are 7. 1, 2, 3, 4, 5, 6, 7. Okay, I listed them all there. Those are what we call diatomic molecules. And typically these are named blank gas, right? Oxygen gas, hydrogen gas, right? If we see that phrase, we would know that it is going to be H2, right? If we see hydrogen gas, we know it's H2. It can't just be H. Okay, so here's how we pick them out on the periodic table. Excluding hydrogen, so let's ignore hydrogen for just a second. You see where nitrogen is? So our molecules are nitrogen, oxygen, fluorine, chlorine, bromine, iodine. What shape does that make? Feels like it makes a 7 to me, right? This and this. Feels like it makes a 7. Agreed? So nitrogen, oxygen, fluorine, right? If I connect all those, it makes a 7. That tells me my diatomics. There are 7 of them. So it makes the 7 plus what other one? Hydrogen, right? So that's how you can remember which are your diatomic molecules. Starting with nitrogen, draw your 7, and then you've got hydrogen over there as well. Okay, are we clear on that part? Okay, so there are 7 of them. So if I say water mixes with chlorine gas, I would know that it's not just Cl, it's Cl2. Okay, it has to exist in a pair. Okay, so we've done a bunch of introduction here on chemical reactions. Now let's actually get to the balancing part. This is the part, okay? When we balance chemical reaction, our goal is to satisfy the law of conservation of mass. And we said that the law of conservation of mass tells us whatever goes in has to come out, right? That's what the law of conservation of mass tells us. And so we will see kind of a formula for a chemical reaction, and we have to build the ratios to ensure that whatever's going in is coming out, right? It's like we have the recipe without the measurements, right? We've got to know how many cups of flour to put in and how many things of eggs or whatever, right? That's what we're doing here is they give us the recipe, but they don't give us the numbers that go with it. So we have to check that. That's essentially what we're looking at here, okay? When we do them, we're going to balance each atom one at a time. So we're going to check the nitrogens, then check the oxygens, check the hydrogens, things like that. If you have a polyatomic ion that appears on both sides of the equation, you can keep that together. So let's say I see nitrate on both sides. I'm not going to break it into nitrogen and oxygen to balance. I'm just going to say I have 2 nitrates and 2 nitrates, right? 2 sulfates, whatever it might be. I'll give you the option whether you want to break them down further, but I think for us, we'll be able to recognize that and keep them together. You'll see what I mean here in just a second. Balancing reactions is very much like puzzle work, okay? It might take you more than one try, but there's only one right answer. There's only one way. And there's really never an excuse for you to miss a balancing reaction question because there's a way to check your answer, right? You literally have to count your atoms on both sides. And as long as they're equal, you know your reaction is balanced. So there should be no reason you miss questions about balancing reactions, okay? But it might take you more than one try to get there. This happens often. If there's challenging problems, sometimes we miss things, sometimes we miscount. We have to maybe do it multiple times. But it is very much like a puzzle. Okay, so a couple things that we have to attend to here or think about. We never add coefficients in the middle of a chemical formula. So if I have KNO3 and I know like I need 2 nitrates, I can't just put a 2 right there, right? That doesn't work. I also cannot adjust its formula and say, oh, I need 2 of them. No, right? I can't change the formula once it's correct. If I need 2 nitrates, I put a coefficient, and so that also means I have 2 potassiums as well, right? It might affect both. So then I have to go back to the drawing board and make sure that my potassiums are balanced. But I cannot adjust one without adjusting the other, right, if it's a compound. Double check your chemical formulas, blah, blah, blah. We never change subscripts in a correct chemical formula. So if, like I said, if this was, I can't just change that to be a 2 to make it balance. No. Right? We have to make that work. And then we can reduce coefficients if they are all reducible by the same number. So let's say I had 4A plus 2B yields 6AB. Let's say I had balanced my reaction and that's what I got. Can my coefficients all reduce by the same number? Yep, so I should really say 2A plus 1B yields 3AB, right? I accidentally overshot it. It doesn't happen a lot, but if it does, you just reduce them down. Okay? So I gave you a lot of information and a lot of kind of rules to follow. Let's actually put some into practice here. Okay? I'm going to start with a simple one. I've got copper plus silver nitrate yields copper nitrate and silver. Can you tell me what type of reaction, what category of chemical reaction does this fall under? Combustion, synthesis, decomposition, single displacement, or double displacement? I think it's single displacement as well. Single displacement, right? We see that copper and silver are switching places, right? Okay, very good. Let's go into the balancing part of it. I'll show you my process for balancing. You can use something similar. You can use something different, whatever you prefer. But my theory is to make a little list of what we have. I have a copper. I have silver. And I have nitrate that stays together on both sides, don't I? NO3 on both sides. Do we agree with that? If you wanted to, you could break down and count nitrogens and oxygens. But since nitrate stays together, I am going to go ahead and keep it together and count it together. The first thing I do in balancing a reaction is just count what I have. And I'm going to show you this process. Even though this is a simple problem, we will see ones that are more complex. So you don't maybe you see it right away how to balance it, but I'm going to show you the process I go through. How many coppers do I have on the left side of my reaction before I put any coefficients, right? I assume that what coefficient is present in each of these. I assume that there's a 1 there. And if there's a 1, I don't have to write it. But I assume that there is a 1 in all of those places. Okay, so to start out, I have how many coppers? 1. How many silver? And nitrate? 1. Okay, on the right side of my reaction, I have how many copper? 1. How many silver?
1.
And nitrate?
2.
2. Okay? The 2 only applies to what's in the parentheses, not copper. So you see, I counted the left side, I put it on the left side of my list. I counted the right side, I put it on the right side of my list. That's why I did it that way. Now, I check my list. Are there any elements here that are not balanced? Or polyatomic acid? Nitrate is not balanced. So can I go over here and just write a 2 like that? Nope, I can't adjust it. So if I need 2 nitrates, I change my coefficient. You need to change your coefficient first. Then you display or represent that change in your list. So by putting a 2 there, I not only changed nitrate, but I changed silver as well. Right? Do you see what I'm saying? By putting that coefficient there, I not only have 2 nitrates, but I have 2 silvers also. So I have to change both components of my list. Now in my list, I check and see, well, what's not balanced now? Silver. And so in order to get 2 silvers on the right side, I put a 2 there. That changes that to 2. And so am I balanced now? Yep, coppers are good. Silver is good. Nitrate's good. So there is my balanced reaction. And can I reduce all my coefficients down? No, because there are 1s in the other ones, right? So I can't divide this by 2. People try to balance their list before they put anything in the reaction. I'm going to very strongly encourage you, change the coefficient up top first, then reflect that change in your list. So after you change your coefficient, then recount. Don't just try to make the bottom work, right? The bottom is just your workspace for what's happening up top, okay? All right, let's try another one here. Aluminum plus bromine equals aluminum bromide. What type of reaction is it? Synthesis, right? It's building it up. This is synthesis reaction. Okay, we have aluminum and bromine. We have just 2 different elements here. That's it. So I'm going to start by just counting them. How many aluminums do I have? 1, and bromine I have 2. On the right-hand side, how many aluminums? 2, and bromines I have 6, okay? So I don't have anything balanced as of right now, okay? Yeah, Owen.
You put a 2 and a 4.
So I'm going to put a 2 here, which changes my aluminums to 2. And what coefficient needs to go here to make, I need a total of 6.
3.
I need a 3 there because we multiply that out. So instead of having 2 now, I have 6. And so that balances my reaction for me. Okay, we feel comfortable there? We need to make sure we understand that this and this are multiplied.
Is the S
All right. L stands for liquid. All right, KBr. So K plus 2 bromines equals KBr. So let's go ahead and do this one as well. I have potassium plus bromine. Right, some of them might be so easy you don't need the list. That's okay. Okay, but I want you to know how to use it. So I have 1 potassium, 2 bromine, 1 and 1. So what's my solution here? What's the thing I need to change? Bromine on which side? No, not on the left. On the right. So I'm going to put a 2 there, which changes potassium and changes bromine. And so now I'll come over here and make sure that potassium matches as well. Right, I'm always going to change my coefficient before I change my list. Right, the list is just a running tally of how many of those things you have. Right, it's just a workspace. Okay, go ahead and try this third one here on your own. Try this sodium plus water. Try that one on your own. This one's a little trickier. Here we're going to run into the same thing with our oxygens. Do we see? The left side will always be even, and the right side starts out odd. So we've got to think about, you know, a coefficient to go there that would be even. But that doesn't have to be your first step. I like to look at my list and say, which is the easiest change I can make? Right? I want to make the easiest change first. Dealing with my oxygens is not the easiest. right? But my carbons might be an easy one, or even my hydrogens might be an easy one. Okay? Think through this process with me. I want you to just watch right here. What would be my obvious choice right here to make my hydrogens balance? I have 6, but I need 6, but I only have 2. What coefficient would I put there? A 3. But what did we just say it has to be? Even or odd? So if it's supposed to be a 3 and I know it has to be even, I'm going to double it to make it a 6. Right? Do you see what I'm saying? I'm thinking one step ahead, knowing that the 3 is not going to work because I know it has to be even. So I'm going to try to think one step ahead there. And so that'll make the left side not balanced, but that's fine, right? I can bounce back and forth. Those are just things that I want you to start being able to identify a little bit quicker, okay? Which I know we're still right at the beginning of it, but that's my thought process through there. So this would be 12. My oxygens would be 2 plus 6, which is 8. Okay, so it seems like I made it worse before I made it better, but that's okay. All right, so now I'm just going to kind of keep working on seeing what else I need to balance. 2. So oxygen was not paired with anything on the left. I left my oxygens till the end because I knew I could change this coefficient without it affecting something else. So if you have an element that's kind of by itself, I would recommend leaving that one till the end. That way, if I have to make a change there, it's not going to trickle down and mess up something else. Sometimes you don't always get that option, but that's a tough one. Did we get there on our own? Maybe I might not have given you quite enough time. That's tough, tricky. Okay. All right, we already did this one. Let's try this last challenge one on our own, and then we've got a CK12 assignment after that. So once you finish this challenge question, you can start working on your CK12 assignment. I want you to commit like a maximum of 5 minutes to this one. Okay, if it takes you more than 5 minutes, then call it and start working on your CK12. But let's see if we can get it done here, within the next few minutes. I'll jump start it up on the board here in just a couple minutes. Okay, so get your count going. But it's hard to follow balance and reaction after the work's been done. Are any of us to this point and we're stuck? Mm-hmm. Okay, so here's where you have to just kind of take a risk, okay? And you just change one, right? You could double it. You could change your coefficient. I know, or I have a feeling that this oxygen is my problem here, okay? Do any of you else feel like that? Like that's my problem. So I don't know off the top of my head what the answer is even supposed to be, right? Because I just don't know the answer to every problem before I start. But if I know that's my problem, I'm going to go ahead and just throw in a 2 right there and see if that can kickstart something else for me. So you could try a different coefficient there if you wanted. But if I know that oxygen I think is my problem, I'm going to start there and see if that can jumpstart that for me. Okay? Because we said this is like a puzzle, right? So you don't see it right away the first time, and that's okay. I mean, that's true for me as well. So that changes my hydrogens and that. Okay, so I think that's what did it, right? Okay, by adding that 2 there, I needed to change my hydrogens again. And by doing that, it caused me to change my nitrogens again, right? It caused me to bounce back and forth. So problems like that are tricky, and they can cause that puzzle effect, right? We got to go